All right, so today we're going to jump in and look at boiling and condensing. I believe this is chapter 13 in your textbook. So for those of you that are actually doing the requested readings, thank you. For the rest of you, shame on you. But as we round the corner in this class, there are just a few things that I like to discuss. Okay. So boiling and condensing heat transfer. So when investigating let's say boiling heat transfer, it is important to note the influence of temperature and pressure on a vapor liquid equilibrium system. Such that at any given temperature and pressure, I can consider a system where my temperature is below the saturation temperature. I have some appreciable vapor pressure, and I know my vapor pressure is also below the saturation pressure, right? So in this instance, let's say I've got a pool. I know it looks like a drum. Oh well. Fill it with some water. And maybe a fun floaty toy. So in this kind of system, I've got liquid water in the pool, and I have water vapor in the air. If I'm running my pool right, the temperature of the water in the pool is going to be below the saturation pressure. There's going to be appreciable vapor pressure, but it won't be saturated unless you're here in Oxford in July. So let's just say it's not Oxford in July. And so at this liquid vapor interface, I can expect evaporation to occur. That means that in an effort to achieve a true vapor liquid equilibrium, I'm going to be having some of the liquid water enter the air as water vapor, right? Because PVAP is below PSAT. This differs from boiling in that boiling occurs at a solid liquid interface. Because, or when, a liquid comes in contact with a surface or solid object, at a given temperature, T sub S, I'll make this more of a complete sentence. That is sufficiently higher than the liquid's saturation temperature. So, recap. Evaporation is at the liquid vapor interface, as the liquid and vapor attempt to achieve some form of equilibrium. Boiling is different because we have a liquid in contact with a surface or a solid that has a temperature above the saturation temperature. You're simply saying Ts is greater than Tsat. And we can quantify the heat flux due to boiling as some heat transfer coefficient times that gradient that we see, Ts minus Tsat, which is equal to H times delta T excess. Right. And this is application of Newton's law of cooling. Any questions so far? You guys following along okay? Thumbs up, thumbs down. All right, appreciate it. Okay, so we can break up boiling into several classifications. Where an example of some of these is pool boiling. In the absence of fluid flow, if a system or a liquid is boiling, we consider that pool boiling. Good example of this is water in a pot. Trying to make your weekly or daily ramen. And this is different or opposes to pool boiling or flow boiling, where we have the presence of fluid flow. A good example of this is within a heat exchanger. Right? So you can consider like a reboiler from a distillation tower is going to exist for that fluid as a form of flow boiling. We can also consider what's known as subcooled boiling, where the average temperature of the liquid is below the saturation temperature. And this differs from saturated boiling, where the average temperature of the liquid is approximately equal to the saturation temperature. And so depending on the characteristics of our system, whether it's pool boiling, flow boiling, subcooled, or saturated, we can expect differing behavior associated with the rate of boiling, as well as the anticipated heat flux and heat transfer within that system. So,
When do we
go ahead.
see subcooled boiling and saturated boiling?
Oh, that's what we're going to talk about next. How those genres of boiling or classifications influence what we see within a boiling system. So that's a good question. And so let's first consider, because we're going to kind of go through the stages of boiling. So the first stage would kind of be in a subcooled state. So my question for you guys is, what would happen, or what happens to a liquid as it comes to a boiling, so to speak? And this is just general anecdotal discussion. We don't even have to be super scientific mathematic. I assume you guys have boiled water at some point. Y'all have moved past toast and Eggo waffles. So what do you typically observe when you get that pack of instant ramen going?
Convection starts to occur, at least
All
in the
right.
pot.
So we have some type of convection. What kind of convection do we see?
Natural convection.
Yes. Thank you, Nicholas. Convection happens. Natural convection. Then what happens as you keep boiling it?
Bubbles start to form in the bottom.
All right, so initially we've got the liquid, fire. You are correct. And then we start seeing the little natural convection. Then we have bubbles form. Where do the bubbles form?
At the solid liquid interface.
All right, at the solid liquid interface, and as Carly said, at the bottom. So going back to my little pot right here. I'd start to see some bubbles, right? What happens to those bubbles? I have no idea why a sudden YouTube link showed up.
As they grow, they begin to rise. Or once they reach a certain size, they begin to rise.
So the bubbles form. What happens to them initially? Do they rise or do they just hang out?
They hang out at the bottom.
Hang out until they're big enough, right? All right, so what happens as they rise? You guys are doing really good. I like this. Just for you, I'll draw your little top ramen on the table. The little foil packet. I know you guys secretly come from my artwork. So we get bubbles forming, they get big enough, they start to rise. What happens to those bubbles?
Once they reach the surface, they pop.
So bubbles, if they reach the surface, enter the vapor phase. Or essentially they are a vapor phase, but they kind of leave the system, right? I would say they evaporate, but they're already in the vapor phase. Right? And if they fail, what happens? What happens to the bubbles once they fail?
They return to the liquid state and just act as convection currents.
Okay, so they kind of collapse, right? They condense and collapse. All right, so now the trickier question is, why do they condense?
Because the water pressure is higher than the vaporization pressure.
Not necessarily.
Because they're heating like the bulk water phase and transitioning like a phase change to a temperature change.
There you go. Because as that bubble rises, right, it's emitting the heat into the bulk fluid. And so you have those bubbles rise, and as those bubbles rise, you have heat transfer from that vapor to the liquid. And what you'll find is the majority of heating of the bulk fluid happens by these bubbles. And so it heats, it rises, you get the vapor. So we can recap. First, we get natural convection. Then we get bubbles to form. As they form enough, they'll essentially detach from the solid liquid interface. They'll rise. Initially, the majority of them will collapse, and you'll have this essentially heating mechanism. Then as the temperature of the bulk fluid gets high enough, the bubbles basically get enough time to actually escape and enter the air. So what happens when we keep heating it? And I'll just say this, or keep heating arrow. So we got bubbles. There's some are popping, some are getting out. What happens if I keep heating it?
the boiling occurs more rapidly.
All right, so I get more bubbles formed. Greater amount of boiling occurs. I wish I didn't do that. All right. And so if we were going to look at this, we can quantify all of this phenomenon as a form of one of several boiling regimes. To illustrate these boiling regimes, we can refer to what we see in slide 5 in the lecture 17 notes. And so this first image shows kind of that introductory stage after we've gone past this natural convection. We start to see bubbles form and break off from the surface. And as we continue boiling, we see the picture in the top right, where we start to see more general boiling of the majority of the liquid at the solid liquid interface. And if we continue to let this system boil, we get to what we see at the bottom picture, where the majority, if not all of the liquid at that solid liquid interface exists as a vapor. And so what we find is one of several boiling regimes, where the initial state of our fluid exists in what's known as a natural convection boiling state. So actually, I'll give you a break. And now we're going to talk about more specifically the boiling regimes. And I'll even back up a little further than that. I know you guys hate it when you take notes with me sometimes. Primarily because the nature of the boiling regimes is highly dependent on our delta T excess, which is once again that Ts minus Tsat. Because what we find is as the temperature of the bulk fluid increases, so too does the temperature of the surface. Because you have to consider, in the system, heat is being added to that surface by an external source. And as the bulk temperature increases, the heat transfer from that surface to the liquid is going to decrease enough such that the temperature of that surface itself is going to increase. And so what we find is as we move through these boiling regimes, the temperature of the surface in relation to the saturation temperature is going to increase. And so I'll write that down and say it again. And so what we find is as we progress through each boiling regime, we find that the surface temperature increases. As well as the delta T excess. Because once again, that saturation temperature isn't going to change. So even though we're heating the fluid, the bulk fluid temperature is going to rise. But when we're focusing on boiling, we're looking at the temperature gradient in relation to that saturation temperature. And so what that means is we see an increase in T sub S, Tsat doesn't change, and therefore delta T excess changes. What we find is that 4 different boiling regimes exist. That describe a typical boiling system. And these regimes can be characterized by what's known as a boiling curve. So I'll scroll up and zoom out a little bit so you guys can jot down all of this information. All right, so we can look at what a typical boiling curve looks like on slide 4 in our lecture notes. And what we find are the 4 regimes of boiling, quantified by natural convection boiling, nucleate boiling, transition boiling, and film boiling. What we've discussed in terms of our adventures in making ramen thus far are the first 2 realms of boiling, that being natural convection boiling and nucleate boiling. And as we see, nucleate boiling can also be broken down into 2 kind of subcategories where the majority of the bubbles will collapse. And then as we get to a high enough delta T excess, we find that the majority of the bubbles will slowly rise to the surface and enter that vapor phase. And as we see, this is all strongly dependent on that delta T excess, because the delta T excess, as we stated by Newton's law of cooling, is going to directly influence our Q boiling, or our boiling heat flux. A couple things that we'll get to here in a second is the implication of what's known as the maximum heat flux, how it relates to film boiling, as well as this lead-in frost point. So with this curve in mind, let's take a step back and discuss each of these regimes and how they can influence what we expect within a boiling system. So as I stated previously, the first regime we can consider is what's known as the natural convection boiling. And so what we find is that in this regime, we have no bubble formation. As the bulk fluid temperature is sufficiently below the saturation temperature such that as that fluid gets heated at the bottom, natural convection is able to keep the fluid circulating such that no appreciable amount actually vaporizes at that solid fluid interface. We also find that delta T excess is fairly small, right? Once again, because we have that presence of natural convection. So we see about a 2 to 6 degrees C excess in temperature, right? And once again, as I stated, we have fluid motion due to natural convection. Then, as we continue along our boiling curve, we get to what's known as nucleate boiling. In this stage, bubbles form and initially collapse in the fluid. As the heat flux increases, we find that more bubbles form and reach the liquid vapor interface. Right, so that means, as that heat flux goes up, we find that more better vapor formation and more essentially bubbles are able to escape the system. And in this case, the delta T excess is somewhere in the ballpark of 5 to 30 degrees C. So
Is that regardless of fluid, or is this just for water?
regardless of fluid. Good question. All right. So when we get towards the end of nucleate boiling, we reach what's known as the maximum critical heat flux. And it's called the maximum critical heat flux for a couple of reasons. The biggest is what we find, and this serves as a border or a tipping point between nucleate boiling and film boiling. And the important thing to identify here and realize is that the transitional boiling region is skipped. And so if I were to go back to my boiling curve, what we see is that, here I'll give you a good pen color to kind of get this. The typical path is in boiling, 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 looks like this. And so what we find is that our system will immediately jump from C, our maximum critical heat flux, to point E in the film boiling regime. And the other implication of this is our delta T excess at the maximum critical heat flux is somewhere on the order of 30 degrees C. What do we see for the delta T excess in film boiling at point E? What?
1,000.
There you go. Thank you. Thought we were going back to that dead body problem. So we see the delta T axis jump from 30 degrees C to 1,000 degrees C. Now, how many materials do you think can handle 1,000 degrees C?
A few. Very limited.
Very few. And what means is that our delta T excess rapidly rises, such that oftentimes the surface and heating element itself
Are you writing? You're still on the PowerPoint.
thank you. Is destroyed. This is also why we call the maximum critical heat flux the burnout point, because the element will literally burn itself out with the rapid rise in temperature. Now, to understand why this happens, we have to take a look at what we find at the very end of our nucleate boiling regime. And so if I were to zoom in at that pot of boiling water that you guys apparently forgot about, as this gets hotter and hotter, we start to see more and more bubbles, correct?
Yeah.
Thank you. And so what we find is as the surface gets hotter, those bubbles become more and more numerous, such that there comes a point where what's at the surface of that liquid fluid interface is no longer liquid. And what we get is essentially an entire interface that is entirely vapor. And so now what we have is heat transfer from the solid to a vapor, and essentially nucleation off of this vapor film, which constitutes the onset of film boiling. The issue that we have, though, is the energy required to boil a liquid is extremely high, and we quantify it through our enthalpies of vaporization, correct?
Yes.
And when that energy is no longer going into vaporizing the liquid, it's going into increasing the temperature of the vapor at the interface. So we have a transition here in heat transfer from a situation of Q is equal to M lambda to Q is equal to MCP delta T, right? Because we're going from, okay, we're boiling liquid to all of a sudden at that interface, we're heating a vapor. And what do we know about the heat capacity of gases and vapors?
Much, much smaller than liquids.
Yeah, they're relatively small, all things considered. And so every little bit of heat that gets added to that vapor is going to cause a really high jump in the temperature of the vapor. And that jump in the temperature of the vapor is also going to result in a subsequent jump in the temperature of the surface. So what we go is we end up no longer boiling our vapor, we end up literally just cooking the element in the surface itself. And so what happens is we have burnout of the surface. Does that make sense? I know it was a little weird and zoomed out. And that's why, for all intents and purposes, when we operate our systems, we're going to be operating in this nucleate region. So I'll say operate here. Because like I said, once you get past that maximum critical heat flux, you get into film boiling and your system gets destroyed. You have a bad day. And so what typically happens in a system, if we're wanting efficient heat flux and boiling heat transfer, we identify, well, what's the maximum critical heat flux? We identify, okay, let's operate 70, 80% of that. And so you essentially get, a high degree of your driving force, high amount of heat transfer and boiling, but you're safely away from that maximum critical heat flux such that you don't run the risk of running into film boiling. And so to kind of wrap up summarizing this, I can say for film boiling, we have a stable vapor film between the solid and liquid. However, if the materials can handle it, what you find is that you can quickly reduce the heat flux in film boiling to reach the minimum heat flux. Point known as the Leiden-Frost point. Which if I go back to that lecture slide, that means if your system doesn't have a burnout situation, what you can do is instead of running into a burnout situation, oh, that's interesting, it won't let me get rid of it. What you can do is you can get here and then quickly reduce your heat input. And what you can find is that you can get even better performance because you're operating at this minimum heat flux point at the region between what's known as film and transition boiling. And transition boiling is mainly just, you have kind of elements of both nucleate and film boiling. Sometimes you'll hear it called unstable film boiling, where you're going to have some portions of it going to have a stable film and some form that's going to look more like nucleate boiling. But this kind of operation is typically rare. What you often see in terms of common practice is operation within the nucleate boiling regime. Because once again, it's all about stability. So any questions on these boiling regimes?
I think I might have missed this when you said it earlier, but why do we not want to operate past that nucleate boiling regime?
The issue becomes the the words fell out of my brain. Excuse me. The issue comes when you have the propensity for this dramatic rise in temperature, because as you hit that maximum critical heat flux, going above that causes a jump from point C to point E. And that results in a very dramatic increase of the temperature, the surface temperature of your heating element and surface. And so going from a delta T axis of 30 degrees versus 1,000 degrees Celsius is going to cause a lot of things to get destroyed.
All right, that's all I need to know. Thank you.
Of course. All right, any other questions? Happy to answer. All right, if not, I think that's a really good stopping point for today. Not as far as I'd hoped. And so I think on Friday, we'll get to doing some calculations associated with identifying fluxes in the nucleate boiling regime, as well as the maximum and minimum critical heat flux. So thank you guys for your attention. As always, if you have questions, feel free to reach out to me via email or stop by office hours. I'll be over there in about 10-15 minutes.